Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we will be covering the theories of acids and bases. I'm pretty sure this is not going to be very long either because there's only 3 learning outcomes and it is about something that's pretty simple to explain, so yeah, this is not going to take a long time to finish. So in terms of the theories, there are 3 different theories, which are the Arrhenius, BronteLaurie, and Lewis theories. Unfortunately, I'm not sure if I'm actually pronouncing any of them correctly, so yeah, don't expect me to pronounce things correctly. But anyways, the first one will be about Arrhenius theory, which is probably the most archaic one in the sense, the most simple seeming one in the sense, and it's what we would usually associate with an acid or a base. So if you think of an acid or a base, you would usually think that the acid has got H plus and then the base has got OH minus. So that's basically what the Arrhenius theory is about. So the Arrhenius theory states that an acid will dissociate to give you H plus in water, like water solution, and a base in water solution will dissociate to give you OH minus. So that's the idea of Arrhenius theory. So from this you can say maybe something like HCl to water, it will dissociate into H plus and Cl minus. It's an acid. And something like NaOH will be a base because it gives you a OH minus in water in the sense. So that's the idea of Arrhenius theory. Okay, so the next one, which is the next a newer theory compared to Arrhenius theory, is the BronteLaurie theory. And the idea of the BronteLaurie theory is that instead of putting it as H plus and OH minus specifically, they're more of focusing on the H plus aspect of it. So the BronteLaurie theory suggests that an acid is a proton donor and a base is a proton acceptor. So instead of saying that the base gives you OH minus, it just says that the base accepts protons. And they don't really mention water as a solution, so it could be in any particular solution whatsoever. It doesn't have to be water. So a proton donor, of course, once again you can say HCl is a proton donor, but it is only a proton donor if it's inside a water solution or in a similar solution that makes it dissociate. Likewise, but the real application of this is in terms of conjugate acids and conjugate bases, because conjugate are where they kind of make all those conjugate bonds. You know what I'm sorry, not conjugate bonds, coordinate bonds and stuff like that. So for conjugate acids and bases, you would usually be seeing this in organic chemistry. So things like like phenol and basically any benzene with a group that can give you a conjugate acid or base. You get what I mean in the sense. So if let's say you have phenol and the phenol doesn't have its H plus of phenol in the sense, you know what I mean? Like phenol, when you remove the H, it becomes a conjugate base. But phenol itself, it would be considered like a conjugate acid. But phenol isn't really the best example because it's pretty not the best acid, I suppose. But yeah, it kind of works. Of course, there's stronger ones with like carboxylic acid and things like that, but you get the idea. And if you're looking at ammonia, for example, ammonium ion is the conjugate acid of ammonia, which is the base. So that's what conjugate acids and bases mean. It's basically like the pair of the same, the similar molecule, but one of them is a base and one of them is acid. That's the idea. Because ammonia can accept ammonium ion, and ammonium ions can donate a proton to become ammonia. So that's the idea of conjugate acids and bases. Okay, so the third one would be the Lewis theory of acids and bases, which I think is the most comprehensive and all-encompassing of the 3, because the Lewis theory of acids and bases involves not protons but electrons. So, oh yeah, just in case you didn't know what a proton was, a proton is a H plus ion, so yeah. But anyways, in the Lewis theory, an acid accepts a pair of electrons and a base donates a pair of electrons. And you may be wondering how this works because it's a bit harder to conceptualize than an actual proton or H plus ion in the sense. So how would you understand this? Well, if you want to look at base it on how your understanding of proton acceptors and donors, so basically the acid will donate a proton, right? So when it donates that positive thing, like the positively charged thing, it becomes negative in a way. So you imagine it as it's accepting electrons. Okay, this is just a way for you to memorize or remember which one is which. It's not, please do not use this to explain why it accepts electrons or donates electrons. Okay, so this is just a way for you to remember easily. So if it donates the positive H plus, it kind of accepts it becomes more negative, so it's like accepting a pair of electrons. Likewise, if it's receiving a H plus, it is kind of getting rid of its electrons. Okay, yeah, because let's say let's use the example that they have here. Okay, this one is BF3 and NH3, and there's no like very clear H here to look at, so let me just look at NH3 on its own first. So when you have NH3 and it becomes NH4 plus, what does it do? The N makes a coordinate bond with the H, right? So it's actually giving its pair of electrons to the H. That's why it is being an electron pair donor. The base is an electron pair donor. Likewise, the H is the acid here, so the H plus so it accepts the pair of electrons as it is the acid. So that's why when you look at Lewis acid and bases, you're very likely to see coordinate bonds forming. Although you can use this to Arrhenius and BronteLaurie acids and bases as well. It would be somewhat encompassing in that. And I'll tell you why in a second, but sorry, no, not in a second. After I explain this example, I'll tell you why it works with those two as well. Okay, so when we are looking at the example that they wrote here in the learning outcome, which is boron trifluoride and ammonia and the ammonia atom. Sorry, not atom. Why is there so much of noise outside? Sorry, I got distracted by all the noise. Okay, the ammonia compound molecule in the sense. You will see that ammonia likes to become ammonium ion by forming, because the N has a free pair of electrons there to do coordinate bonding with. Whereas the boron trifluoride doesn't have enough electrons in the central atom, which is the boron. It only has 6, so it can accept another 2 electrons. So the boron trifluoride acts as the electron receiver, the one that accepts a pair of electrons. So it is in this case the acid, and ammonia as an acid-base reaction solely because of the electron pair exchange in a sense, or the electron pair coordination in a sense. Yeah, the coordinate bond formation. So now let me go back to what I was talking about just now, is how you can apply the Lewis theory to Arrhenius or BronteLaurie theory. Okay, so if you're looking at Arrhenius theory itself, which would be, when you put it in water, you get the H plus and you get the OH minus, and you're like wondering, where can it actually donate electrons or share electrons or whatever? Okay, let's just imagine it this way. In the solution, if you're using something like HCl or NaOH, the H plus or HCl specifically, the H plus and Cl minus will first separate out, right? And since they're charged in a sense, they're actually still charged. The water molecules kind of surround them, and water molecules are polar. They're permanent dipoles, and they will actually form coordinate bonds with. It's not coordinate bonds. They'll form hydrogen bonds with the, not necessarily hydrogen. Okay, fine. Maybe with the H plus it could be a hydrogen bond, but no, it's not a hydrogen bond. It's more of a permanent dipole and ion bond. Yeah. that's what it is. Yeah, it forms that kind of a bond, and it forms like this spherical thing around it. And that's how it dissolves. In a sense, it stays dissolved because of the water. So in that scenario, is there some kind of electron donation? Okay, not really. But you could consider it in that sense, because the water, like when you write water in acid, right, you would write it as H3O plus. So it would be like a water molecule, and the O has two free pairs of electrons, so it can do a coordinate bond with one of them and form and join with the H plus. So in this case, the water acts as the base and the H plus acts as the acid. If you're looking at the Cl minus side of things, that would be the, well, Cl has a lot of free electrons in it because it's a full 8 electron in its outermost. And when the water molecules come along, and of course it can really attract the water molecules. Yeah. Okay, I don't know where I'm going with this, but you get the idea. I do not want to waste any more time on this. But with the H plus, I think it's pretty clear. You can see that this may actually work with the Arrhenius theory as well. So for the BronteLaurie theory, I think we kind of explained it just now, like how it works. If you're donating a proton, it's kind of like accepting electrons, and if you're accepting the proton, it's kind of like donating electrons. So yeah, I think it kind of encompasses everything. Don't worry. So yeah, this is pretty much it. You just need to know what each of the theories mean and be able to write them down in the exam, and as well as use the terms Lewis or BronteLaurie, especially when you're doing organic chem or talking about conjugate acids or bases or Lewis acids and bases. So yeah, that's pretty much it. This is a pretty easy topic in terms of the learning outcomes, that is. Of course, when you're doing the actual exam, you should be able to recognize what each of the molecules or compounds that you're seeing are. So with that, I hope you found this video useful despite my very sad attempt at trying to encompass everything at the end. And if you found this video useful, please press the like button and subscribe. And with that, I would like to say thank you and bye!